Alright, how's it going everybody? We are here. I'm making this video on Thursday, April 15th. Today we're going to talk about section 9.3, which is going to cover imaginary or complex numbers, the complex plane, and de Moivre's theorem here. So today's going to be quite a bit different than some other days that we've seen. What we're going to do is we're going to take some idea that's probably going to be new to some of you, not new to others. It's certainly the fact that this will be new in the concept's relationship to trigonometric properties here. And so today we're going to have a little bit of an exploration of imaginary complex numbers. And again, importantly, we're going to see their relationship to trigonometry and in particular to our polar form stuff that we've been looking at for the last couple of days. So the question that we should be asking ourselves are, what are imaginary or complex numbers and where do they live? Which is sort of a weird way to phrase that there, but I want to talk about kind of what does it mean to even, what are these numbers that we're referring to here? So to start with this, we're going to solve a couple quadratic equations. We're going to do some, not trigonometry, we're going to do some algebra to see when we might see these numbers arise. And then today what we're going to see is kind of managing some math with these numbers, seeing what types of things they can help us to describe. So in these three examples right here, we want to solve each of these equations. All three of these equations are quadratic, which means we can either solve them by factoring or we can solve them maybe perhaps directly or maybe using the quadratic formula here. So this first one, x squared minus 1, since this is the difference of two perfect squares, x squared is a perfect square, 1 is a perfect square because 1 times 1 is 1. That tells me that I can factor this guy here as x minus 1 times x plus 1 is equal to 0. And the zero product property here is going to tell me that x is equal to 1 or negative 1. Either of those x values would make this true. So notice here we got two what we would call real solutions. We had real valued numbers to start with and we got real solutions. On the other hand, if we come over here and I say I want to solve the equation x squared plus 1 equals 0, this is sort of like saying what number could I square and then add 1 to the number and get out 0. Well, you can clearly see that we're going to need x squared to be negative 1. But what you know is that every time we square a number, we get a positive number. Well, the slightly more technical thing to say there is every time you square a real number, you will get a positive number. However, I feel like I should technically algebraically be able to take the square root of this number here on both sides and arrive at the solution x equals plus or minus square root of negative 1. Now, if you've taken algebra, then you know in algebra class that we define the square root function to be a function that only takes in positive real numbers and only spits out positive real numbers. However, what we're going to discuss today is that numbers that have a component of a square root of a negative in them are still going to be useful for us describing, we'll talk about what we're describing here, but we're going to see that these numbers are useful to help us describe things like a rotation. So what we're going to do here is we're going to name this thing. I just wrote it wrong already. We're going to name the square root of negative 1 to be I. And so I'm saying here that our solutions to this equation, if I call the square root of negative 1 just I standing for our imaginary numbers, and by the way, imaginary complex are two descriptors meaning the exact same thing. Unfortunately, those are pretty unfortunate names. The guy that kind of first defined all this stuff right here, he did not name them either of these things. He did not call them complex numbers or imaginary numbers. He called them, I'm trying to remember here, I feel like he called them like adjacent numbers or something. He said that they lived adjacent to the real numbers or something like that. That name never stuck, and some other contemporaries of his named them complex and imaginary numbers, and he hated that. And the guy that kind of first kind of formalized a bunch of discussion associated with this, he despised the names that ended up getting given to them by other people. But it's the names that stuck. So you shouldn't think of these as imaginary as in non-existent. You shouldn't think of these as complex as in complicated. Both of those are bad names here. All we're talking about is things like, you know that there's no real number that you could square to get out a negative, but there's still going to be use for us in representing the quantity that would exist if we could define such a thing right here. And we'll see a little bit more of that today. So here's our first imaginary number. It's the square root of negative 1. It's the simplest possible imaginary or complex number that we could have, and therefore this gets the special name of I, this script I. So you're going to see lots and lots and lots of I's in this section, and I is always referring to the square root of negative 1. Let's see it crop up in one other context text right here. Here's one more quadratic for us to solve. Looking at this guy, I can see that I can't factor this one, I don't think, and I can't solve this directly because there's more than one instance of x, so I can't just directly solve for x. So I think I can go to the quadratic formula for this guy. So I can say that x equals, what do we got? Negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's just going to be 2. It looks like I'm getting negative 2 plus or minus the square root of 4 minus 20 over 2, which looks to me to be negative 2 plus or minus the square root of negative 16 over 2. And so here again you can see we're getting the square root of a negative number. And so let me do a smidge more algebra with this to manipulate the square root. What we in general like to do is to always state our complex numbers in terms of I. So I think that what I can do here is write this as negative 2 plus or minus the square root of 16 times the square root of negative 1 all over 2. You know the square root of 16 is 4. Square root of negative 1 is what we've called I, all divided by 2. So it looks like we're getting negative 1 plus or minus 2i. This would be my complex valued solution to that quadratic right there. Negative 1 plus or minus 2i. And that I, again, coming from the negative that is underneath the square root right here. So we can name anything that we want, like who really cares, right? Like we called this quantity I. Great. Does it mean anything to us? What does it mean to multiply a number by I? Now we're defining I to be the square root of negative 1, so it should be the case that when we multiply by I, it should be sort of like multiplying by negative 1. But honestly, if I had to say to you, hey, what does multiplying a number by negative 1 do, like graphically, I think it would be difficult for most of you to try and answer that. And so what I want to do is picture this on a number line. We'll draw some pictures right now, and we'll also go to Desmos for a little bit of help with this guy right here. So here's kind of the way that I think about this. If we imagine starting with the number like x equals 2, I can picture where this is on a number line, right? X equals 2, it's sitting right there. There's our x equals 2 value right there. Here's our number line. And what I could imagine that we're going to do now is we could multiply by negative 1. And that'll bring us to x equals negative 2. And when we get to x equals negative 2, it's pretty easy for me to graph this on the number line. Sitting right there. And so what I can see has happened right here is that number has been sort of flip-flopped over the line x equals 0. So it looks like it performed a reflection over x equals 0. But the question I have is, over x equals 0. Through where? Where was it? Like, and here's kind of my beef with this. Did this dot at 2 just simply disappear and then reappear at negative 2? Did it perhaps slide across the axis through 0 and get to negative 2? Like, where was this dot? Did it just disappear and reappear at the negative 2 location over there? That feels kind of weird to me. We can also picture this being like a whole interval of numbers. We could picture this as being like x is greater than or equal to 2. And if I draw this on a number line, I can see that 0, 1, 2. If we're greater than or equal to 2, then that means that I'm like shading this region of the number line that's over here, right? And if I multiply that entire inequality by negative 1, then we're going to arrive at the quantity x. Now you guys know that when you have inequalities and you multiply or divide by a negative, it will flip the direction of the inequality. So this will give me x is less than or equal to negative 2. And therefore, being less than or equal to negative 2 should put all of those points that we saw before over here. So again, when we multiplied that inequality by negative 1, did it just disappear all of our points on the right and put the infinite number of points on the left? I kind of like, I don't really feel like that's what's happening, right? Like where were all those numbers for the instant that they weren't at the positives and they weren't at the negatives right there. Through what space were they moving to get there, right? When I say through where, through what space did they move to go from the original location to the new location associated with that multiplication by -1? So what I feel like is happening here to me is that it seems like what we're doing is we're rotating all of these numbers around to land back on the other side of the number line, right? That's sort of like what a reflection is. But the thing that's weird here is that I only have an x-axis. I don't even have a y dimension through which to move. And so the question is, what action should we get by multiplying by I here? And by the way, I said that we'd go look at this in Desmos, so let's kind of do that real quick. If we come over here in Desmos, I can do a similar sort of thing as to saying, you know, if I want to do, for example, a number, A, times like the number 2, I can make that a point right here, and we can add a slider for this guy. We can see it creates a nice little green point for us right there. And what we know that we can do is we can slide up or down. So the more we multiply by does seem to be sort of sliding us along right here. But this is a little bit different when we multiply by a -1, that it brings us over to the other side. And I think the thing that I can kind of show with this is that maybe we can go from -1 to 1 with a step size of 2, meaning the only two possible values are these two. And it just seems a little strange to me that multiplying by 4, I can imagine that is stretching me 4 times more in the direction that I'm already going. But multiplying by a negative doesn't necessarily seem to be doing a stretching, because again, if I currently have the value of 2 and I multiply by -1, what I don't think is happening is that our number gets down to being as small as 0 and then gets as big as 2 away on the other side. I think that the number should maintain its 2-ness the entire time, 2 being a distance from 0, but it should just be at the opposite side of 0 once we've multiplied by the negative. So this is sort of this like very, very strange question that I'm asking. Like, what does it even mean to multiply by a negative? And the point is that I'm trying to say to you is, I feel like when we start with the number 2 and multiply by a negative, we should maintain the 2-ness the entire time, but I also don't feel like the number just disappears and just reappears as -2. So it feels to me like even though a reflection is a appropriate descriptor of what's happening when we multiply by -1, a reflection through where? Through what space did we move through to get from +2 to -2? Can you draw for me the path that you think that this point took at +2 to arrive at -2? And again, if the path that you're going to draw is on the x-axis, then you're claiming to me that by multiplying by 2 by -1, that would be you saying to me that the number first drops down to 0, then it increases back in magnitude again to get back to -2. And I don't think that multiplying by -1 makes us go through 0 to get to some other value. That seems weird. So again, even if we're reflecting, a reflection has to travel through some space. And I'm saying, through what space are we traveling? So here's the way that I like to think about this. If we think about this as a rotation by 180, the reason why this works is because it's saying I can picture the rotation to where we land back on the x-axis again. But I'm going to say that same question again. Through what space did we just travel if we're thinking about this as a rotation? We literally only have an x-axis right here. You can't just invent a new dimension to travel through, right? So where did it go? So here's what I'm thinking to myself. What if this is how we think of multiplying by an entire -1, then we should realize that I, being the square root of -1, should be only 1/2 of one rotation. All right, so the important thing here is that I is the square root of -1, and the other way to write a square root is a 1/2 power. So in a sense, when you multiply a number by I, it's like multiplying by half of a negative. And so if it's like multiplying by half of a negative, then maybe what that means is we should only do half of the rotation that we saw was previously associated with multiplying by +1. So what I'm thinking to myself is now we take this number of 2 on the number line, and we can go ahead and multiply by I. then where should we land? Well, it seems to me like we should be landing at x equals 2I. And the question is graphically, where is that? Well, here was my 0, 1, 2. What I'm picturing is that this thing did half of its rotation that it was going to do, right? I'm picturing this being like a rotation out here where we land back on the other side. Well, it seems like it's only going to do half of that. So the strange thing that's going on here is we're saying, where is this? What dimension are we even measuring this stuff in right here? And it appears that there is maybe some complex numbers that live adjacent to, I should say, like sort of perpendicular to the real number line right here. Let me get that 2I a little bit further away right here. Budging up against my graph. So we can then see things like, it seems to make sense to me then, if we're going to think about this as being how we describe half of multiplying by a negative, then I could maybe think to myself things like, where is negative 2 to the 1/3 power? We should do 1/3 of one rotation, right? So instead of being right here, or excuse me, okay, let's just write this as, just to get rid of the numerical confusion right here, -1. If that's where 1 is, then this is like saying do 1/3 of a negative, and so we should conceivably end up at doing 1/3 of a rotation, that where if we did all three parts, we would just land back over here at -1, right? So multiplying by I seems to be indicating to us amounts of rotation to do. The reason why you've never thought of it that way is because, multiplying by negatives in general seems to be indicating to us do some amount of rotation. The reason why you've never thought about it that way is because pretty much your entire life you've always multiplied by an entire -1, which has always landed you perfectly right back on the same number line that you were previously on, right? Because that's going to indicate to us to do a full 180-degree rotation. If we multiply by any other amount of -1, like half of it or a third of it, like we've done at the bottom of the page down here, then that should say you're not going to land back on the number line that you had originally started on because you didn't do enough rotation to get back over there once again. So basically this is saying a more generic description of multiplying by certain amounts of -1 should always indicate rotation, but it's very much hidden when you're always multiplying by a complete -1, which is what you've done every time you've multiplied by -1 so far in your life, is it's a one whole -1, so it's an entire 180-degree rotation, which landed you always in a very convenient spot, back on the real number line. It therefore seems like all these fractional amounts of -1 that we could multiply by are all not necessarily going to land us back on the real number line out there. Because we didn't get enough rotation to land back over there again, right? So, in general, all imaginary or complex numbers are of the form z equals a plus bi, where we refer to a as the real part and b as the imaginary part. This right here, by the way, is called standard form. We'll write some in other formats as well. And we should also say we can graph complex numbers in the complex plane. This is really easy. The only thing that's a little bit weird about this is that, as you can see, we're just graphing a single number as a point rather than an ordered pair. So this is our real axis. This is our imaginary axis, or our complex axis right here. And for example, if I wanted to graph this z equals a plus bi, then I could go to a is my real component, b is my imaginary component, and here is the single number z equals a plus bi. So graphing its real part and its imaginary part. Notice over here, that's exactly what we did. For our first number, x equals 2, it only had a real component to the number. There were no I parts, and so we only graphed the number on the real axis. Once we multiplied by I, there were no more real parts. There's only an imaginary part, and so we only graphed this number. I didn't even finish graphing it right there on the vertical component right there with the 2I, right? So graphing imaginary numbers, exactly the same thing as just graphing an XY coordinate, except that you are treating A as the X coordinate and B as the Y coordinate, and that's so standard that these are often written as x plus yi, and that's a good way for us to think about relating those to our basic graph locations that you guys are already used to out there. So a plus bi, you go to a on the x-axis, b on the y-axis, but now we're thinking of these as the real and imaginary axes. They're measuring two different components of the number. How much real stuff did it have, A? How much complex stuff did it have, B? And we're putting that in two-dimensional space because there's two features that are required to describe every imaginary number. So our next topic associated with these imaginary numbers is, since complex numbers seem to be helping us describe amounts of rotation, it seems reasonable that we should be considering their properties when we're in polar form, because polar form is where rotation is most easily described. So let's go ahead and see what it looks like to write a polar form of a complex number. So in doing so, we're going to identify some properties of complex numbers. So these are 4 properties that we should look at of all complex numbers. 1, that powers of I repeat, and then 3 properties of general complex numbers of the form a plus bi right here. So let's take a look at this. So one thing I'm seeing is this. If we're talking about multiplying by I or other fractional powers of -1 indicating rotation, what you guys know about rotation, because it's what we've been talking about all semester, is that if you do some amount of rotation, you're going to repeat the exact same thing over again. We've seen this with our sines, our cosines, our tangents, everything else. They're all repetitive, they're all cyclic, they're all periodic. If this is indicating rotation, then these should also be periodic, right? There should be some amount that we could do this to where we get right back to where we started. So here's the thing I'm thinking to myself. If multiplying by -1 does a 180-degree rotation, this makes sense because you know that if you do a 360-degree rotation, then your object is back in its original setting. Similarly, multiplying by -1 twice is the same thing as multiplying by 1, which leaves a number alone. It leaves it in its original position. Furthermore, you know that -1 to the 1/2 power is the same thing as square root of -1, is the same thing as I. And if this did what we're essentially amounting to be a 90-degree rotation, my question is, how many times do you need to multiply by I to get back to where you started? Well, if a 90-degree rotation is what you get by multiplying by I once, then you should need to do 4 total 90-degree rotations to return back to your original number, suggesting to me 4 multiplications by I, or I to the 4th power, should be back to leaving our number alone, not changing anything. That would be just a multiplication by 1. So let's check this out real quick. I'm just going to make like a table. I to the 1st, I squared, I cubed, I to the 4th, I to the 5th, I to the 6th, I to the 7th, I to the 8th, and it's going to go on and on. And my question is, how can we simplify all of these guys? I think they're all going to simplify nicely since they're just powers of a single number here. So I to the 1st, that's just I, but remembering that I is the square root of -1, my question to you is, what do we get when we do I squared? Well, we're clearly just going to get -1. We squared a square root, right? So now knowing that I cubed is the same thing as I squared times I know that I squared is -1, and I know that I just write as I, so -1 times I should be -I is the same thing as I cubed. And then finally, for I to the 4th, and it's not obvious that this is a finally step right here, but I to the 4th I can think of as I squared times I squared. I squared, we have already decided, is -1. -1 times -1, that's just +1. So exactly like we saw with our rotational idea here, multiplying by I 4 times should do 4 90-degree rotations, which should bring us right back to where we started. And we know that if you want to leave a number alone, you can multiply it by 1. So this is in total agreement with that graphical perspective that we had. Now, if I want to think about even higher powers of I than this, I can think of I to the 5th as I to the 4th times I. And I know that I to the 4th is just 1. So multiplying I by I to the 4th is like leaving I alone. It's multiplying it by 1. So notice we're back around at I once again. You should notice it took us 4 additional powers of I to repeat the cycle. Now I can think of I to the 6th as just being I to the 4th times I squared. I know that I to the 4th is 1, so I don't even need to think about it in the multiplication. I squared is -1, so this is like saying, what's 1 times -1? And you're going to tell me -1. And not too surprisingly, I, -1, I, -1, the pattern is repeating out here. So it seems like I to the 7th, playing all these same games, is I to the 4th times I cubed. I to the 4th is just 1. I cubed is -I, and that's all we're going to get right here. And then finally, you multiply by one more factor of I, and maybe I could think of I to the 8th if I wanted to as I to the 7th times I. If I to the 7th is -I, multiply by an additional I, we now have negative I squared. I squared is -1, and we're taking the negative of that, and that gets us back to +1. So we can see that we're repeating every 4. That's kind of our big takeaway here. All right, so one very important thing to notice as a feature of this imaginary or complex number I is that every time you take 4 powers of it, it's going to repeat its cycle once again. So therefore, it should be reasonable for me to ask you literally what's any power of I that I want to ask, and all you should have to do is chop off any additional any powers of groupings of 4 at a time to reduce yourself down to just one of the base cases right here, I to the 1st, 2nd, 3rd, or 4th. Those are like your 4 base cases, and this pattern will just repeat itself over and over and over again. So that's one real important feature. We'll come back to this one. This will be a really important thing for a later example here. Another property that we want to identify of our complex numbers is their magnitude. When we graphed our complex numbers a moment ago, one of the things that we identified was where it is located in space, right? So if this is going to be our A and our B right here for Z being equal to A plus BI, what we might want to know is the magnitude of Z is going to indicate to us how far is Z from zero. So this is typically indicated as absolute value of Z, and that's because absolute value measures distance from 0. And so it should be the case that how far are we from 0 here? Well, we know this from our polar stuff last week. We should be the square root of a squared plus b squared units away from 0 here. Occasionally, this is written as exactly what we know this to be as r. So when we're talking about the magnitude of a complex number, we often use absolute value bars to indicate that, because what the absolute value function does, and a lot of people want to tell me the lame version of what does absolute value do, which is it makes a number positive. That's not what absolute value is doing. It is measuring how far are you away from 0. You should notice here we're sort of in a 2-dimensional setting, and so it requires the Pythagorean theorem to measure how far away we are from 0, which is the number that sits at the origin right there. So this is how we can compute the magnitude of a complex number, is by finding how far away in the complex plane is a plus bi away from the origin right there, and we can do that with a little Pythagorean theorem. Another important feature of imaginary numbers is that they all have a conjugate that is very much worth identifying here. So the conjugate of z equals a plus bi is z, and we put a bar over the top to indicate the conjugate, and it'll be a minus bi, and vice versa. If we had a minus bi, then we'd call this a plus bi. It's the same number, except with the sign switched in between. Who cares about identifying the conjugate and switching the sign? Why? Multiplying by a conjugate does something a little special. Let's see what happens here. If I do z times z bar, that should be the same thing as a plus bi times a minus bi, and let's see what we get when we FOIL this guy out right here. I'm going to get a squared, I'm going to get a plus abi, I'm going to get a minus abi, and I'm going to get a minus b squared I squared. Now, 2 important things here. One, ABI and negative ABI are going to cancel. And what do we get over here? Negative b squared I squared. Well, I know what I squared is. We talked about this a minute ago. Since I is the square root of negative 1, to square I just undoes the square rooting. We're just going to get negative 1. So this is really like negative b squared times negative 1, which gives me positive b squared. You should notice that when we multiplied a complex number by its complex conjugate, what we got back was a real number, right? So one thing to think about here is that the conjugate is an important term for us to consider with complex numbers or imaginary numbers, because it's sort of, if you multiply a complex number by its conjugate, you're guaranteed to turn into a real valued number. Multiplying a complex number by its conjugate makes it a real number. Right, there's no I left over in that anymore. The two cross product terms canceled out, and we got an I squared, which is really just negative 1, which is a real number. It sort of completed the rest of the rotation associated with that. So it is often the case when dealing with complex numbers that dealing with their conjugates is regularly something that is of use for us to identify. And so this is a bit more of just a definition thing right here. Just knowing, if I say to you, hey, what's the conjugate of that number that you're looking at right there? All you're going to do is swap the signs in the middle. If it's positive, make it negative. If it's negative, make it positive. Finally, we want to see if there's something other than the standard form available to us here. Standard form is sort of what we're thinking of as being like our Cartesian coordinates when we graph it. However, since imaginary numbers seem to be indicating to us concepts surrounding rotation, I think it's more helpful for us to maybe to think about our complex numbers being in polar form. So our polar form of our complex number, we're just going to think about z being like this a plus bi, or as maybe being like our x plus yi. And I remember that x equals r cos theta and y equals r sine theta. And so maybe we can go ahead and just make this substitution in here and say z equals r cos theta plus r sine theta times I. And then typically we'll write this ever so slightly different. I'm noticing that both of these have a factor of r. So I'm going to factor that out and write this as cosine theta plus I sine theta. So this can be an alternate way that we can represent a complex number. And what this is going to tell us is how far is that complex number from the origin in the complex plane, and what angle do we need to rotate to land at that number. And you can see that just like this number has currently been defined in a rectangular coordinate system, we could also think about opening up some amount of angle and traveling some amount of radius to get to that location. So this is its polar form rather than its standard form right there. We're going to talk kind of right now about why do we like polar form so much better. And again, I'm going to say it again. Since complex numbers seem to be indicating to us ideas surrounding rotation, it's going to be much more natural for us to do math with imaginary numbers when we are in polar form, since what they're describing as rotations. Polar form is better at discussing those rotations. We're going to see that if we try to just always stay in standard form to do math with complex numbers, the math is going to get really hard because rectangular coordinates are not best for describing rotation. Polar is. And so our math is going to be much, much easier dealing with complex numbers often when we are in polar form. So real quickly, let's identify some of these characteristics. So we just looked up here, ultimately our properties of the complex numbers in general were the magnitude, conjugate, and polar form. It's also a general fact about imaginary numbers that they're always, powers of I are always going to repeat every 4 powers. But these are sort of the features of every imaginary number that we might want to identify: magnitude, conjugate, and polar form here. So let's go ahead and find each of these properties of a complex number as a little example, and then we'll look at some arithmetic operations with complex numbers. That's where we're going to see that polar form is definitely our friend in this case right here. So first things first, our magnitude. Magnitude, remember, is just a measure of how far are we from 0. So we have that our number here goes negative 2 root 3 in the real direction, and it goes 2 in the complex direction here. So I think I can say that how far is our imaginary number from 0 should be the square root of the sum of the squares of these two numbers. All right, this is just the Pythagorean theorem in action right here. So what am I going to get? Let's see, 2 root 3 squared. So when I square negative, it becomes positive. When I square 2, it becomes 4. When I square square root of 3, it becomes just 3. 4 times 3 is going to give me 12 for that guy right there. Our other one here, 2 squared is 4. It looks like this is just the square root of 16, which is just going to be 4 for our magnitude of z. Now you should notice that this is also what we described as like our radius term. It's our distance from the origin. That's going to be really helpful when we go to write this in polar form. Let's quickly state the conjugate here. It won't be directly helpful for us in getting into polar form, but that's okay. Since z is negative 2 root 3 plus 2i, if I asked you to identify the conjugate, we would say that z bar, the conjugate, is negative 2 root 3 minus 2i. And again, notice that we're not negating the whole number. I'm not multiplying the a term by negative 1. I'm just swapping the sign that's between a and bi. That's all we do to get the conjugate right there. Finally, to get into polar form, we need r and theta. And what we kind of want to remember for ourselves is that our polar form here is z equals r cosine theta plus I sine theta. Well, the good news is that we already found r. To be 4. So what I'm thinking to myself is, let's take this number right here, z, and let's factor 4 out of it, because I want my z to ultimately be written as the magnitude, r, as being a number that is factored out from the other terms right here. So let's factor out 4 from z. So if I do this, I'm going to get z equals, so what do we got? We got negative 2 root 3 plus 2i. I'm going to write this as z equals 4. So I'm doing a division process here, right? So that's negative 2 root 3 over 4 plus 2 over 4i. And now let's simplify this guy a little bit right here. Definitely need some more room. And what do we see? It seems to me like this is going to be 4 times negative root 3 over 2 plus 1/2 I. And what I'm kind of seeing here is that we're trying to make this look like z equals r times cosine theta plus I sine theta. Well, it seems to me like in that case right here, it must be the case that our cosine of theta is negative root 3 over 2, and that our sine of theta is going to be 1/2. So my question to you is, what angle is going to give us those properties right there? Well, I can see here that with the cosine being negative, that means we're on the left half of the unit circle. With sine being positive, we are on the top half of the unit circle. So I'm picturing on my unit circle here, we're going more to the left than we are going up. These are obviously numbers that I kind of recognize from our general angles right here. So it seems to me like there should be some angle in the second quadrant where we've gone left by root 3 over 2. We've gone up by positive 1/2. And I think I can identify this to be, 90 degrees plus 60 degrees, so either 150 degrees. Or we could think about this as, let's see, 1, 2, 3, 4, 5 pi sixths as theta here. And now that I've identified what is my r term, my radius, by finding the magnitude, and by factoring out the magnitude, I was able to set up a system of equations that can help me identify the angle. I now know that my polar form for this complex number can be written as 4 times the cosine of 5 pi sixths plus I sine 5 pi sixths. Now, here's where you should be at right now. You should be saying to me, well, okay, you should be saying to me, all right, Tony, I guess I can do that. I can like find that angle right there, sure. but who cares? Why would we ever want to write a number in this format if I could write it in just a plus bi format, which honestly, I mean, this is definitely simpler. Sure, there's a square root in it, whatever. Why would I like undo this number of 1/2? Why in the world would I switch from writing a number as 1/2 to writing it as sine of 5 pi sixths? You should be saying to me right now, that doesn't make any sense. I would never write the number 1/2 as sine of 5 pi sixths if I could just call it 1/2. The reason why this is a valuable move for us is because converting into polar form is going to make our arithmetic operations so much easier for us. In fact, I'll go so far as to say I straight up can't do most complex number arithmetic if we're not in polar form. It gets to be way too complicated. In polar form, we're going to see that a bunch of these things are going to fall out to be very, very simple. So let's go ahead and take a look and see what it looks like when we try to do multiplication, division, and take powers of complex numbers here. All right, so again, this polar form is clearly more complicated than its original standard form. But by converting into polar form, we are given much easier access to doing arithmetic with this number than we would have been able to do in our original standard form. So this is not as easy for reading, but this is much more convenient for doing. And that's why we're going to like this form. So let's see why this is going to happen here. So what I want to know is, what does it look like for us to do multiplication, division, and exponentiation, or take powers of complex numbers here? So here's the thing that I'm thinking. Let's look at these guys currently in just polar form right here, because I want you to see the really nice stuff that's going to happen. All right. So what I'm going to do is I'm going to call Z1, I'm going to call this R1 times cosine of theta 1 plus I sine of theta 1. And we'll call Z2 R2 times cosine of theta 2 plus I sine of theta 2, right? So we've got two very generic complex numbers, Z1 and Z2, both in polar form. What I want to know is, what does it look like when we do Z1 times Z2, right? The whole question here is, what does it look like when we do multiplication of two complex numbers? So I made two generic complex numbers. I put them in polar form because I know where we're going, and I want to see what happens when we multiply them together. So what we should be getting here is we should be getting R1 times cosine of theta 1 plus I sine theta 1 times R2 times cosine of theta 2 plus I sine of theta 2. And I just want to do some rearrangement right now. What I'm kind of seeing happening here is two things. One, the R1 and the R2 are just constant coefficients out front of both of their groupings. So one thing I'm seeing is that I can just bring both of those out front to just be the constant coefficient together, R1 times R2. So that's really convenient. If we know R1 and R2, and when we multiply together our two complex numbers, your new radius or magnitude is just the product of the previous radii or magnitudes. That's cool. But what's going on here with these angle terms here? Well, it looks like I need to FOIL out this stuff right here. Cosine theta 1 plus I sine theta 1, cosine theta 2 plus I sine theta 2. So let's go ahead and FOIL out these terms here. So first says we're going to get cosine of theta 1 times cosine of theta 2. Outer says cosine of theta 1. So we're going outer says cosine theta 1 times I sine theta 2. So I'm going to get plus I cosine theta 1 sine theta 2. Inner says I'm going to do the inner two terms, so it looks like I'm going to get an imaginary term again because there's an I on this one. Plus I sine theta 1 cosine theta 2. And finally, last, you should notice here that when I multiply I sine theta 1 times I sine theta 2, we're getting an I times I, which is I squared, which we know is really negative 1. So I times I is negative 1. That's going to make this a subtraction now. And we're just going to get sine of theta 1, sine of theta 2. So a very typical thing to do when dealing with complex numbers is to always write them sort of in standard form, or at least in standard form in the sense that I want my real terms together and I want my complex terms together. We can see here that the middle two terms, the O and the I in FOIL, ended up being complex. We can see that the outer two terms, the F and the L in FOIL, end up being real. The first one was real because we multiplied a real part by a real part. The second one was real because we multiplied an imaginary part by an imaginary part, and the imaginary times imaginary gave us just -1, a real number right there. So if I were to group these up, then we're going to get R1, R2 times, I'm going to do these in groups, cosine theta 1 times cosine theta 2. And my other real part is the minus the signs over here. Sine of theta 1, sine of theta 2, plus I times, and again, I'm writing this sort of like in standard form, right? A plus BI. I'm getting the I's all grouped out there. These are all the terms that have complex parts. That's these two terms in the middle. So I've factored out their I, and now I just need cosine theta 1, sine theta 2, plus sine theta 1, cosine theta 2. Now, I'm going to ask you, where do you recognize these groupings of sines and cosines? Have you ever seen anything that looks like this? Have you ever seen anything that looks like these two groupings right here? And the answer is, heck yeah, you have. You definitely have. I'm going to show you where you've seen them before. All over the place over here. You've seen these guys. So our first grouping of terms looks like cosine, cosine minus sine, sine of their respective angles. Cosine, cosine minus sine, sine. And I've seen that before. There it is. Cosine, cosine minus sine, sine looks like that's really the sum formula for cosine. That's cosine of theta 1 plus theta 2. So I've got my first term here. Now what's going on with the second term? I know that's going to be I times something. What do we get? Cosine sine plus sine cosine. Cosine sine plus sine cosine. I'm seeing over here, let's see, cosine sine plus sine cosine. Seems like that's exactly our format right there. It looks like this is the sum formula for sine. Ooh. Ooh, ooh, ooh. Could that have worked out nicer? I don't think so. So notice how, and I know that this looks like a lot because we're writing a lot right now, but stop and like see this for the incredibly nice result that this is. This is why we like the polar form stuff so much. Notice that when we multiply together two complex numbers in polar form meaning we have identified the radius and the angle required to get to that location in the complex plane. If we multiply the two numbers, all we do is multiply together their R values, which you're going to clearly see because we're going to be in polar form. We multiply the R values and we add the angles. And that's it. And we're done. That's how we do multiplication in polar form with complex numbers. Multiply the radii, add the angles. That's easy. And I hate calling things easy because I never want anybody to feel bad. This is easy. You're doing a single multiplication and a single addition to multiply two complex numbers in polar form. And the reason the math works out so nicely is because complex numbers are describing rotation, and so using polar form to describe them is going to give us the simplest types of operations arithmetically to manage them, because polar form is designed to deal with angles. That's exactly what it exists for. So that's really cool. And we're not going to get such nice things that work out like this if we were in standard form, because standard form isn't designed to deal with rotations. Now, what's going to go on with division out here, I think that you should make a guess. If when we multiplied together two complex numbers in polar form, we multiplied their radii and we added their angles, then what do you think we're going to get if we were to do this whole process with a division instead? Well, hopefully you're not terribly surprised to find that we're going to do the division of their radii. What's going to happen with their angles? Well, if you wanted to kind of repeat some math that's like this, the math will be a little bit harder since we're dealing with a fraction instead of a product, but you could do the identity verification there, that we're going to just get the subtraction of the two angles in here. So the fact that multiplication and division are so simply defined as long as you're in polar form is really good news for us, because that says it's actually pretty easy for us to do multiplication and division of complex numbers. But again, all this requires is for us to be in polar form. So if I ever say to you, hey, divide these two complex numbers, if they're in standard form, like we stated at the very, like we state like up here, this is standard form, it's very often helpful to first convert to polar form, then do the mathematical operations, because we get these really nice rules for complex numbers out here for how these things work. Now, the even better one here, the one that is actually restrictive for us, is doing exponentiation. But what we know is that exponentiation is just repeated multiplication. So what that means to me is that if I were to do like z to some power, like z to the n power, then what's that going to do? Well, all I got to do is look up at my multiplication rule. That would be like doing z times z. Well, in that case, you get r times r, which would be r squared. That's because we only did a multiplication of two terms. We got a second power. Well, here, if we're doing a multiplication of n terms, we should get an nth power. So we're just going to get that. We're going to get r just gets taken to the nth power. You don't have to do anything, any kind of weird thing with that. If I'm trying to take a complex number to the sixth power, then you're going to convert it into polar form and take the sixth power of your radius, and that'll be the new radius of the sixth power term out there. What's going to happen on the inside to the cosines and the sines? Well, we saw up here that when we did multiplication, we added together the two angles. Well, when we're doing exponentiation, that's just repeated addition. That's adding the same, that's multiplying the same number over and over and over. So we're going to add the same angle over and over and over. And what would you say if I said, hey, let's add that angle to itself 5 times? Well, you would just say, oh, so it's 5 times the original angle? Yeah, exactly. So here we're just going to get n theta, right? That's theta plus theta plus theta n times plus I sine n theta. So really easy for us to even do kind of crazy powers of exponential crazy powers of complex numbers. As long as they're in polar form, it's easy for us to do this. It is hard for us to do this if we're not in polar form, because again, imagine I said to you, take the sixth power of this number right here. If you wanted to do this the FOIL way, you would have to do so much work. You'd be sitting there multiplying this out for 15 minutes. On the other hand, if you converted it to polar, you just do a simple power out front, a simple multiplication on the inside, done. It's very easy to make these arithmetic operations happen, only in polar. Polar is nicer because complex numbers describe rotation, and so does polar form, right? X and Y are not as helpful to us here because imaginary numbers don't tell me about perpendicular motion. They tell me about rotation. So let's go ahead and see an example of this. Let's write this complex number in standard form. And notice, very importantly, the complex number that I'm referring to has a cube on it right there. So what I'm thinking to myself is that this is what I'm going to call z cubed, is that thing right there. So that says to me that what z really is z is just the 2 times cosine 20 plus I sine 20. So if I want to cube that, I'm just going to use my exponential rule that's sitting right above it. To get z cubed, I'm going to do 2 cubed. So my rule here says the power on z is equal to the power on r. My rule here says whatever angle you used to have on the inside, theta, multiply it by what the power was. This is z to the n power. It's now the multiplication inside of here. And we know that that follows because just like exponentiation is repeated multiplication, multiplication is repeated addition. And here's the addition that we're repeating right there. So that says to me we should be doing cosine of 3 times 20 plus I sine 3 times 20. And we're basically done. This is 8 on the outside. This is a cosine of 60 plus I sine of 60. And the only other thing is we wanted standard form here. So this is saying get out of polar form to end the problem. I want this in terms of A plus BI, not in terms of our polar form stuff here. So then I just got to ask myself, well, what is cosine of 60? What is sine of 60? And I can see that if I just look on my unit circle over here, looking at our 60-degree angle right here, it seems like the horizontal amount, the cosine, is the small amount. So that's going to be our 1/2. Therefore, the sine of 60 has to be the root 3 over 2. And to get then into our A plus BI format, I can multiply the 8 through, and that's going to give me 4 plus 4 root 3 I. And there is z cubed in standard form right there. We wrote this complex number in standard form. I first identified what was the number without the power. I didn't want to think about the power for 1 second. Here is sort of our baseline function, or our baseline number. To cube the number, we cubed the radius, and we multiplied by 3 the angle, and then we just evaluated to get back into our standard form right here. Just to get standard form, we wanted, this is our A plus BI right there. So I can see what my real component is. I can see what my complex component is right there. All right. Now, we're going to do another one, but what I want to show is that there is technically another way that we could do this, but it is not really viable to do it generally. 50th power right here is no problem for me if we're in polar form. 50th power here, if I try to stick it out in standard form, is really, really, really going to suck, and it's not something I could really do in general. So that's why I'm saying here, polar form is your best friend on this one. It does make all of the math as simple as we could possibly get it to be. So, let's do this first way. Powers are easiest in polar. This is our first route to our solution right here. So let's go ahead and do this first way to say, listen, I'm thinking to myself, or I'm telling you, it is going to be easiest to do arithmetic with complex numbers if they're in polar form first. So let's identify R. We've got that z equals 1 plus I. And by the way, I always like to think of this as being, this is like my z to the 5th. That's the number that I want to actually describe. So that's helping me think of just the imaginary components without the powers as being like z. So this is going to have that A equals 1 and that B equals 1. Remember that B is how much complex stuff do you have? I have 1I, so that's why B is going to be 1 right there. Therefore, the magnitude of z, or what we might call r, is going to be the square root of 1 squared plus 1 squared. Well, 1 squared for each of those is just 1. So the square root of 1 plus 1, that's just going to be the square root of 2. So I know what my magnitude is. Now let's factor out r from z. And find theta. I want to take my z here as 1 plus I, and I want to factor out that root 2 from it. Now I know that factoring is a division process, so this is like a 1 over root 2 plus 1 over root 2I. And I'm thinking to myself, I feel like I've seen the number 1 over root 2 before. I'm thinking to myself, this is actually what we got before we simplified into root 2 over 2, right? That's the same number right there. If you were to multiply these fractions here by root 2 over root 2, which is 1, root 2 over root 2 is 1, it's the same number divided by itself, then you're going to get a root 2 on top, and on the bottom, root 2 times root 2 is just a whole 2, right? So it seems to me like we're going to get the statements then that are going to say, let's see here, let me back up here, let me get some color in here. This is my r, this is my cosine theta, plus I sine theta. So it seems to me like I can make the statement then, I'm looking for a theta such that cosine theta is root 2 over 2, and such that sine theta is also root 2 over 2. Fortunately, I definitely know the angle that makes this happen. That one's a pretty easy one. It's pi fourths. Notice that both of these are positive, so it has to be our first quadrant angle, and it's where the cosine part matches the sine part, has to be where the angle is equally split. 45 degrees down there, 45 degrees up there, right? So we get that pi fourths as our angle. So we've got our polar form of z. That is going to be z equals 1 plus I equals, and it looks like we found that r is root 2, and we found that this is cosine of pi fourths plus I sine pi fourths. And again, you should be looking at this and saying, but Tony, 1 plus I is clearly the easier way to write what this number is. The polar form is clearly a really convoluted way to write what the number is, but arithmetic with polar form numbers is much, 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 much easier. Again, our second way that we're going to do this is just to FOIL this beast out, and that's going to suck. We're going to have to multiply out all these terms, and that's not a reasonable thing to do. And again, that's just a fifth power. Imagine this was a 50th power. You're not going to FOIL that out and do 50 sets of multiplication and make no mistakes. It's not reasonable to do. So in polar form, this is where it's now much, much easier to take our powers. Fifth power. So we've got that z is going to be equal to root 2 times cosine of pi fourths plus I sine pi fourths. Therefore, z to the fifth, which is what we really wanted to find the whole time, is root 2 to the fifth times cosine of 5 pi fourths plus I sine 5 pi fourths. And now we can go ahead and simplify this number down to something a little bit easier for ourselves here. So one thing I'm thinking to myself is, what's up with root 2 to the fifth power right there? You should think to yourself, if we're going to multiply together 5 root 2's, what did we really get? Well, those two make a 2, those two make a 2, and that's just a root 2. So it looks like this is 4 root 2 is my better way to write root 2 to the fifth. Now, cosine of 5 pi fourths, this is one of our pi fourths, so I think I'm getting some version of root 2 over 2. But I 5 pi fourths is somewhere else, right? So I'm thinking 1 pi fourth is here, 2 pi fourths, 3 pi fourths, 4 pi fourths, 5 pi fourths. So 5 pi fourths is in the third quadrant, so we're going to get negative root 2 over 2 for both of them. And now, just to simplify this guy, I'm going to multiply it all back out and get into standard form. Now, 4 root 2 times root 2. Well, the root 2 times root 2 is 2. Divided by 2, those 2's cancel, and it looks like I'm just getting negative 4 for my real part. Exactly the same math over here. I'm going to get 4 for my imaginary part, but also the negative. So it looks like that fifth power right there is going to be the same number as just negative 4 minus 4i. So again, identifying what our steps were here was to say, convert the number into polar first, then take the power, then convert back to standard form, because that's honestly where it's simplest to write the number. I mean, obviously 1 plus I is very, very simple. Negative 4 minus 4i is very, very simple. Square root of 2 times cosine of pi fourths plus I sine of pi fourths is not simple, but it's where our arithmetic is simple. So it's harder to state it. It's easier to do things with it in polar form. So we get into polar form to do the math, and then we get right back out of polar form again, because standard form is just the easiest one to read. Right? So let's go ahead and do this another way, and let's go ahead and see that it's technically doable, because 5 isn't too huge of a number, but if I had said to you 50, then there's no chance that you'd be able to do this. And I'm going to say to you, this is only going to be easy because I've got, 1 and 1 is my coefficients right here. It's not going to be easy otherwise here. So let's do 1 plus I times 1 plus I, or rather, here, let me say it this way. We need to account for a grand total of 5 of them, right? So 1 plus I to the 5th is going to be equal to, let's write this as 1 plus I times 1 plus I, and then times 1 plus I cubed, right? So there's all 5 powers that I have right there in total. I'm just saying, let's do this 2 at a time right here so that we can see where these terms are going to be. So I'm just going to FOIL out just those guys first here. So this should be, first it says 1 times 1 is 1. Inner says 1 times I is I. Outer 1 times I is I. So I'm going to get plus 2I. Last says I times I, which is negative 1. And so I'm going to get a negative 1 there. And this is times 1 plus I cubed. Now I can simplify this a little bit right here and say this is actually, it seems like this is just 2I. When I multiply 1 plus I times 1 minus, or sorry, 1 plus I times 1 plus I, it seems like I just got 2I because the first part of positive 1 and the second part of negative 1 canceled right there. So what I'll now do is I'll now write this as 1 plus I times I plus 1, times our 1 plus I squared. I'm trying to do this like the easiest way that I can, and I'm obviously going to make this more convoluted now, I think, is what's going to end up happening. But here's, okay, so here's what I guess I'm really seeing. I've already done a 1 plus I squared. And what I got from it was 2I. So what I'm thinking to myself now is this. It seems like this should be 2I from 1 plus I squared. It seems like this should be 2I again from 1 plus I squared. And it seems like we should get a 1 plus I out there on the end. So let me get some more colors here, because I'm being confusing now. Right? So 1 plus I squared was also 2I. And we are keeping this 1 plus I, dragging along. I just put it out there on the end. Now let's do this multiplication. What's 2 times 2I times 2I? Well, it's going to be 4I squared times 1 plus I. And that's going to be 4I squared. Well, that's really just negative 4 times 1 plus I. And now I multiply that out and I get negative 4 minus 4I. So the point is, the other technique over here doesn't really care about what the power is. That doesn't affect the difficulty. If this was a 50th power problem over here, then over here I would just been like, whatever, root 2 to the 50th, cosine of 50 pi fourths, I sine 50 pi fourths, I would have evaluated been done. If this was a 50th power, then we would have had 10 times as much work to do over here. The other thing that happened here is that 1 plus I squared turned out to be a really easy number to do math with, of 2I right there. If this was even just like a 1 plus 2I, then we wouldn't have gotten anywhere near as nice as stuff right here. So this actually worked out to be extra easy because 1 plus I is like a very, very, very nice complex number there. If it had been anything else, again, even just 1 plus 2I, this would have been way, way harder right here. And then 50th power would just be straight up like none of you would get this right without making some small execution errors. This convert to polar first technique says the power doesn't change the difficulty. 50th power, 500th power, all the same level of challenge to me. It's just convert to polar, apply the power, convert back to standard is all we're really doing. So let's take a look at a little diagram of what we did. I'm just going to even get rid of that statement right there, so they didn't quite really do that technique here. So here's kind of what we just did right there. We've got, I'm going to identify, I'm going to make like a sort of a mapping of what just happened. So sort of like 4 different places we could be. We could have our standard form number z. All right, this is like our z equals a plus bi. This is like our z equals r cos theta plus I sine theta. This is our, like our z to the 5th or whatever it is, or a z to the n power. I should just be general right here. And this is also like our z to the n out here. So here's kind of really what just happened. What we wanted to do is we were given a number in standard form, right? We were given 1 plus I, and we wanted to take its power. We wanted to just do this. Get a right, going directly from a standard form imaginary number to a power of a standard form. Again, imagine doing the 50th power of this, and imagine it being not such a nice complex number. Going to get really, really, really difficult. Our goal is just to go from standard form to the power of a standard form, but doing it directly is really, really hard. So instead, what our technique is, much more generally here, is it's more typical for us to, where's our a nice color for ourselves right here, is instead say, convert to polar, take the power in polar, very easy, and then convert back to standard. Right, so this is sort of my diagram showing that we're taking sort of like this little roundabout path often to do this manipulation. We typically start here. Sorry, let me draw. And if we start there, we are looking to end here. Right. So we're starting at this dot, and we want to just go directly to this dot, but it's really hard to do this directly. So instead, what our path was is take our standard form number, convert it to polar, apply the power in polar, which is super easy, and then convert back to standard. And all 3 of these steps collectively often end up being much, much simpler than attempting to just directly take that power right there if we're just hanging out in standard form, all right? So the blue path is easier than the orange path, even though it's 3 steps. And that's kind of my conclusion here. So even though it's 3 steps instead of 1, it's the easier way to do the math. So typically this is the encouraged route to do this. Convert to polar, take your power in polar using our very simple power rule, and then convert back to standard. So our deal here then, coming up next, is this is pretty nice with integer powers. Fractional powers aka roots, this gets harder. Fortunately, we get Demoivre to help us out with roots of complex numbers. So let's wrap up today with the statement of Demoivre's theorem and an example, which is going to help us do a very similar process, but there's going to be one little technicality that we want to keep track of. So let me go back real quick here. When we got our rule for exponents, all we said was, if we're going to do to an n power, we take the nth power on r, we do the nth multiplication with theta right there. If we're doing a fractional power, which is the same thing as a root, right? If you take a cube root, that is the same thing as a 1/3 power. And so here, if I had n being 1/3, it's certainly the case that you're just going to take a cube root of r, and you're going to divide theta by 3. However, there's one additional technicality, and like that's really all that's happening right here. So the roots are almost exactly as easy, but there's one extra thing that's going to crop up in here, which is to say, just like when we go to find our exact solution, or our particular solutions versus our general solutions, we know that we need to add that like plus 2 pi k, and then divide it by that constant multiple that's been inside of our trig function. We need to incorporate that component right here. Demoivre's theorem says, basically, if we're doing fractional powers, that's going to be just as good as when we did our whole number powers up above. We're basically using that same formula, but the one difference is going to be that given a complex number with our typical polar form right there, then what we're going to get is that there are n distinct complex roots of z of this form right here. So that's really saying we should be getting, and this is kind of like my statement underneath, it says, if I ask you to compute the ninth roots, I should say ninth roots of a complex number, then there would be 9 answers, right? Demoivre's theorem says that there are n distinct complex roots for any nth root that you're looking to apply out there. So this mostly agrees with what we see with real numbers. If I said to you, find all the numbers that square to 4, then you would tell me that there would be 2 and -2. And a square root of x is the square root of x is the same thing as x to the 1/2 power. So we should notice here that there were 2 solutions associated with the fact that we took a second root. Right? So similarly, and now the issue is that this breaks down with real numbers when we go higher and higher roots. It's not like there's 3 different numbers that are the cube root of 8 or something like that, but we'll see with complex numbers that is going to be the case. So let's wrap up with our final example today is, let's find all 3 complex cube roots of the complex number -1 plus √3i right here. So as our last example, let's do this. So what we're going to do is we're going to do basically like we did before. Let's convert to polar, apply the power, and then my thing right here says we can just leave it in polar. Let's say convert to polar to use Demoivre's to take the power. And remember, x to the 1/3 is the same thing as the cube root of x right there, right? So fractional powers are our roots out there. So to convert to polar, first, let's go ahead and find r. Z equals -1 plus √3i. So we have that a equals -1, b equals the square root of 3, and we can use our Pythagorean theorem to go ahead and solve for r. So it looks like we found that our r term, our magnitude, our radius is going to be 2. Now let's go ahead and factor out our known r term from z. And use that to find theta. We've got that z equals -1 plus √3i. I want to go ahead and factor out 2 from that. I know that factoring is a division process, so I will divide that by 2. I will divide this number by 2 as well. It seems to me like, given that this is wanting to be in polar form here, this should be r cos theta plus I sine theta. So it looks like we are looking for some angle where cosine of theta equals negative 1/2 and where sine of theta equals root 3 over 2. I'm seeing that that means that our value is to the left and up because our cosine is negative and our sine is positive. So I expect us to be in the second quadrant here. So I'm seeing that our cosine is going to go to the left a little. Our sine is going to go up a lot right there. I think that's our location of interest right there. It looks to me like that was like 90 degrees plus an additional 30 degrees, so 120 degrees. I'll do this one in degrees just because we've done the others in polar here, and both of these are acceptable, I suppose. So in this case right here, so we get z should be equal to 2 cosine 120 plus I sine 120. So we've converted to polar. Now let's use de Moivre's theorem to apply our 1/3 power, right? So we've converted z. So we've got that z equals negative 1 plus root 3I has been converted into z equals 2 cosine 120 plus I sine 120. Now, de Moivre's theorem is going to say, if you are going to do the complex cube roots, we should get 3 answers. We'll call them z1, z2, and z3. They should all have the cube root of our radius as the leading coefficient. And it seems like we want to divide our angle by n, but also track the fact that we should have like a 360k over n there as well. And so what I think I'm even going to do right here is say, you know, this is even going to be like 2 times cosine of 120 plus 360k plus I sine 120 plus 360k. And you guys know this to be true. This is literally just me saying, oh, listen, by the way, if the angle that's inside cosine and sine were 360 bigger, you'd get all the same numbers. That's all I'm saying right there. We can add a whole count of a whole extra revolution if we want. It's not affecting the values that we're getting out here. So now I can find the cube roots. Now I'll get all 3 cube roots. So I'm going to say that z to the 1/3 is going to be 2 to the 1/3 times cosine of, and I'm just dividing this whole thing by 3. 120 plus 360k over 3 plus I sine 120 plus 360k over 3. And let's just do some simplifying here. So I'm going to do one line of simplification, and then I'll state my 3 answers here. And by the way, another way that you could totally write this, it doesn't matter if you write this as a fractional power of 1/3 or literally writing it as the cube root. Either of those are exactly the same thing. I'm fine with either of those. So it looks like I'm going to be getting here cosine of 120 over 3 is going to give me 40 plus 120k plus I sine 40 plus 120k. And what we're seeing now is that there are going to be 3 distinct values where we get 3 actual different angles that are going to be in here. So I'm going to go ahead and call these Z0, Z1. What I should be doing, I think, right here, is I feel like I should be calling this sub k right there. So it's the kth root. I'm looking for the 0th one, whereas k is 0, where k is 1, and where k is 2. These are my 3 different solutions right here. You should notice that if k is 0, we're getting the cube root of 2 times the cosine of 40 plus I sine of 40. If k is 1, then I'm getting the cube root of 2 times cosine of 160 plus I sine 160. And finally, cube root of 2 times, if k is 2, then I'm getting 240 plus 40, which is 280. You should notice that if I let k be equal to 3, I'd be adding 360 to these, and therefore would be exactly equivalent to z0 here. So, as promised, since we were finding the third root, or the cube root of a complex number, we did in fact get three distinct numbers, that all of which we could cube them, and we would get back to our original z. You should notice that if I cubed this number, then think about how this goes. I'm going to talk through this. This is really important that you believe this and you're not just like, I don't know, Tony just did some math and got three answers. Check this out. If I cube z0, cube root of 2 cubed is 2. Well, there's my 2 from z. If I cube this number here, then that means I'm multiplying the inner terms by 3. 40 times 3 is 120. 160 times 3 is 480. 480 is coterminal with 120 because you subtract off 360. 280 times 3 is 840. 840, if you subtract off 720, is coterminal with 120. So it's going to give you the exact correct locations when you cube them, right? You should further notice that where are all three of these things located in space? Our first one is at a 40-degree angle, and it's the cube root of 2 away from the origin. That's z0. Then our next one is the exact same distance from the origin, but it's at 160 degrees. Oop, I'm not drawing my... Don't need that. And my final one is at 280 degrees, which is going to be, let's see, there's 270, so 280 should be sitting somewhere like this right here. You should notice that these are equally distributed around a circle. Z0, Z1, Z2, evenly distributed around a circle with radius cube root of 2 right there. These three angles right here, 40, 160, 280. So this will always be the case when you do this. So again, you should always be able to verify after you do your de Moivre's theorem that you could reapply that power. Just like we took a cube root to get here, you could cube all of these numbers, and when you cube all three of these cubed give us back exactly z. Awesome. So this is de Moivre's theorem, and de Moivre's theorem helps us recognize that we'd better be getting a whole collection of answers whenever we go look for cube roots. You can easily verify that applying a cube to all three of the answers in the box means that all three of these are literally the exact same thing as our original z up above right there in polar form, because 40 times 3, 160 times 3, and 280 times 3 are all coterminal with one another. They're all landing at that 120-degree angle right there. So we're getting out the exact same number when we cube any one of the three of those. These are the three distinct complex cube roots of this value z that we see at the top right here. So this was our little exploration of complex numbers today. You should be able to do multiplication, subtraction, addition, conjugates, magnitude, polar form, standard form, graph in the plane. All these things were relatively easy that we did here today. Our slightly tougher ones were doing powers of complex numbers, which we all know we're all going to go get into polar form when we want to get our powers of complex numbers especially. And we've seen that de Moivre's theorem says, hey, taking roots is basically the same thing as taking powers. You just have division instead of multiplication, except that you have to get whole collection of results, not just one result. So make sure that as you're doing this, you do include your plus 2 pi k or plus 360k, and that is part of the division. A cube root, we did division by 3. If I said find the 18th root, there would be 18 answers, and you'd get the 18th root of your radius, and you'd get your angle plus 360k divided by 18 out there, and you'd list all the possible angles that we could have in here, the angles which are distinct from each other. But if you were to reapply that multiplication by 18, or in our case multiplication by 3 of those angles, all those angles would be exactly coterminal with each other, making you agree that the cube of all 3 of these numbers is the same number. It's z up top right there. So that wraps up our complex numbers. Just as today was probably like mostly a brand new type of day for you guys, where you kind of mostly haven't seen this stuff before. Maybe you've seen I being described in an algebra class, but you probably didn't talk about any of its rotational properties if you've seen it in algebra class. We're also going to talk about something that's probably brand new to most of us in here, which is vectors in our other video this week. So we're going to introduce vectors, which are a little bit different than locations in space, and that's going to lead us into doing a little bit of introduction to some matrix math next week. So we're going to deal with dot products and vectors times matrices, look at some transformations in the plane, see how we can transform a set of numbers through some rotations, some shifts, some scaling, stuff like that, using some matrix things. And that's going to be kind of one of our wrap-up topics here for the semester. So a little bit more confusing today, maybe, but hit me up with some questions. I can always clarify some things about these imaginary numbers. Obviously, de Moivre's theorem gets a little bit hairy right here, but just remember, when you're dealing with complex numbers and you need to do math with them, polar form is your friend. So get into polar form first, then do the math that you need to do if you're dealing with complex numbers. I will see you guys in the next video for vectors. Have a good one.